Hey everybody, hope you're all doing well. I am going to go through the Unit 3 exam practice exam. All right, I already posted the, the answer key on Canvas, and this is going to be the video related to it. If you scroll up, so right now I opened up the practice exam, I'm on page 2. If you scroll up onto page 1, that has a question breakdown of the Unit 3 exam, Fall 25. So do with that what you will, study accordingly. So we're going to start off here. I'll stick with purple. We'll start off here. First section of the exam is going to be some matching keywords. You've had these before. I have picked out the keywords that I personally think are important. Okay, so we have empirical formula, molar mass, oxyacid. This could also appear as oxoacid. Oxo means the same thing, but oxyacid. Salt, polyatomic ion, binary acid, and percent composition. So, know these definitions. You should be good on that section. It's worth a decent amount of points, as it is with every other exam, right? Moving on. So next we have a true-false section, okay? It gives you seemingly what are empirical formulas and asks you, is this an empirical formula? So we could actually go back up, scroll up a little, look at the definition of empirical formula up here at the top. It is the simplest whole number ratio of atoms present in a compound. So when you're thinking of empirical formula, think of lowest common multiple, LCM. Lowest common multiple, yay. So if you think that two of these subscripts could be divided into each other to make smaller numbers, then it's probably not an empirical formula, okay? So let's go through these, and I'm going to zoom in a little bit. So the first one, PCl3. Wow, PCl3. Well, this is an empirical formula. This statement would be true. Empirical formula. We just have a 1 subscript, an understood 1 on our phosphorus, and we have 3 chlorines. There's really no way that could be reduced any further. So, true statement. The next one, S2O4. I immediately think to myself, 2 and 4. Definitely divisible numbers. 2 goes into 4. So I could reduce this to SO2. SO2. Wow, sulfur dioxide. So this statement would be false. It is not an empirical formula. Moving on to the next one, N2Cl5. N2Cl5. 2 and 5 are not divisible by each other. They do not have a common multiple. So there is really no way to further reduce these subscripts. So in this case, the statement would be true. Empirical formula. Wow. Next one is H4O2. That is very similar to the S2O4 that we saw right up here, right? So these have a lowest common multiple, that of which being 2. So if I divided 2 into both of those subscript numbers, it would become H2, and then O. Wow, it's water. Surprise. Wow. So this statement of, is this an empirical formula, would be false. You can reduce those subscripts even further. And the last one, CH3. This is methane. You'll learn about that, organic chemistry and whatnot. But CH3, is this an empirical formula? Similar to the first one, PCl3. It cannot be reduced anymore, right? There's an understood 1 subscript next to this carbon, and I have 3 hydrogens, no way to reduce it. So it would be a true statement. This is an empirical formula. Wow. All right, so those would be some questions that you'll find on the exam. If I move on to our next section here, this is kind of a multiple choice, but there's only 2 choices. So you're given these compounds, and you have to tell us whether it is a molecular or covalent compound, or if it is ionic, right? So these two are paired together, molecular/covalent, right? And then ionic. So you'll just have to put them into categories. So going through them, CO2, carbon dioxide. I ask myself, what is carbon and what is oxygen in terms of the periodic table? Are they metals? Are they non-metals? Because that's what we're talking about with bonds, right? Unequal or equal sharing of electrons tells you polarity, and then the types of things that are bonded together will tell you whether it's molecular and covalent or ionic bonding. So I look at CO2 and I say, okay, carbon and oxygen, those are two nonmetals. Two nonmetals. Their electronegativities are very similar. And so this is going to create a molecular / covalent bond. Wow. Oop, I shouldn't write bond. Molecular / covalent compound, right? It does create those bonds, but we'll stick with that. So this would be your answer. Molecular / covalent. I'm going to start abbreviating this as mole / cove. All right, just for your reference. Down to the next one. Let's see. I have NaCl. That is sodium chloride, table salt. We've talked a lot about this one. If I look at my periodic table, I see that sodium, Na, is a metal. And chlorine is a nonmetal. These have differing electronegativities. Okay, so that means that it will be an ionic compound. Wow. All right, so moving down, we're kind of following the same trend. Check the periodic table. Fe, Fe2O3, Fe is iron. I know that that's a metal. That's a transition metal, right? And then oxygen, that is a nonmetal. That's a nonmetal. It's on the right side of the periodic table. And so again, if you look at NaCl above, you can kind of follow that same trend and go, oh wow, a metal plus a nonmetal, that is an ionic compound. Nice. All right, going down, look at this. So I got some here. KCl. KCl. K is potassium. That is on the left side of the table. That is a metal. And chlorine, on the right side of the periodic table, is a nonmetal. So this will be an ionic compound. Wow. Nice. All right, next one. CaNO2. Ooh, it's a big one. Ooh, it's a big one. Calcium nitrite. So I say, okay, calcium. Calcium, very cool. That's a nonmetal. Well, then I look at this and I'm like, NO2. Interesting. At first I could say, well, nitrogen and oxygens are nonmetals. But if I look at the parentheses that are around NO2, I notice that this is a molecule that's clumped together. It's a polyatomic. So I have a nonmetal plus a polyatomic. And the trick with polyatomics is they're charged. They're polyatomic ions. Okay? So this is going to be an ionic. All right, anyway. H2O. H2O, we've seen this. It's water, right? Hydrogen, although it's on the left side of the table, is a nonmetal. And oxygen is also a nonmetal. So this will be a molecular / covalent compound. Nice. So that is your second section of the online exam. Third section, let's see here. We got counting atoms. Okay, counting atoms. First one, it says, how many atoms of magnesium are in MgOH2? It's asking a specific question. It wants you to count your subscripts and tell how many of that certain element is in a compound. So if I'm looking for magnesium, I can literally just like look right up here and go, oh wow, magnesium, 1. Just one. Just one of them. It's vibing. The next one, how many atoms of nitrogen are in KNO3? Potassium nitrate. That's an important one. Keep it in your minds. How many atoms of nitrogen are in KNO3? Okay, good question. So remember, I'm going to rewrite it down here. When I have something in parentheses with a subscript, this subscript gets distributed. to everything that is inside the parentheses. Okay, so if I'm looking at nitrogen, I'm saying, oh wow, subscript of 2 distributes inside. All right, that means I have 2 nitrogen. I just misspelled nitrogen. Wow. Nice. 2 nitrogen. And that would be your answer. Third one down, let's see. How many atoms of oxygen are in TiOH2O2? So there's one on the exam that looks kind of like this. Okay, it's a little bit more complicated. And you just got to work through it. Remember the distribution rule. So I'm going to pull this out, my OH2, and I will distribute inside. So I know I have 2 oxygens coming from this part of the compound. All right, and then I have an O2 over here. So I have another 2 oxygens. Wow. So just add them together. 2 plus 2 equals 4. We have 4 total oxygens in this large titanium hydroxide compound. So that is third section of the online exam. Lovely, lovely. Moving down, calculate the molar masses of the following compounds. So this is going to require some actual calculation. Okay. What is the molar mass of sulfur dioxide? Now, nomenclature comes into play here because they're not giving you the formula for sulfur dioxide. You have to figure it out. Okay? That's part of the trick. It is multiple choice, but you have to know how many sulfur and how many oxygens are in this compound. So think about it. Sulfur dioxide. To me, this screams 2 nonmetals. I have a molecular / covalent compound. All right. I know by my naming rules that sulfur just has 1. There's no prefix. And even if there was, mono wouldn't be put there. Okay. So just 1 sulfur. And I know I have oxygen. And then I look, I see a di in front of the oxygen. And I go, okay, that means 2. So it's SO2. Wow. Nice. So now I can successfully get my molar mass. MM is molar mass. I'm going to look at my sulfur first. I have 1 sulfur. I go to the periodic table and I check for my molar mass. I see that it's, let's say, 32.07 grams per mole. Awesome. That's just giving me 32.07 because there's only 1. Oxygen, I have 2 of those. And it is 16 grams per mole. That's the molar mass of oxygen. So I got 32 grams per mole. Wow. If you add these together, you're getting 64.07 grams per mole. And this is what you should put as your answer. Obviously, you're going to ask, do sig figs play a role in this? No, they do not. Because the answer keys are kind of keeping in mind that you may or may not know how to name sulfur dioxide. You may not get this correct, right? So don't worry. Use your periodic table. Use the given significant figures of your periodic table, and you will be okay on that part. So let's move on to this next one. Molar mass of nitrogen trichloride. I look, and I'm like, all right, 2 nonmetals, we vibe. Nitrogen is just going to be N. And then I have a tri, which means 3. And chloride, which will be chlorine. So nitrogen trichloride is NCl3. All right, so get my molar masses. I'm going to start with nitrogen. There's only 1 of them. And it is 14 grams per mole. So I got 14. Cool. Then I'm going to do chlorine. I have 3 of those. And the masses of each are 35.45 grams per mole. Multiply it out. I got 106.35 grams per mole. Adding them together, I'm coming out at 120.35 grams per mole for nitrogen trichloride. Wow. Hopefully that makes sense. Just make sure you understand how many there are before you do the multiplying. Okay. What is the molar mass of calcium oxide? I look at this one and I go, oh, okay, wait a minute. We've mixed it up a bit. Calcium oxide. I don't have anything to go off of here. And this is where we have to start kind of pulling our charges. Calcium is a metal and the oxide's a nonmetal. So I know that calcium is calcium 2+. I know oxide is oxygen, and that's a 2- charge, okay? They balance each other out. So our empirical formula here would be CaO. So awesome. I only have to get the masses of one of each. So I'll start over here, and I'll do molar mass of calcium. I have 1 times 40.08, which I pulled from the periodic table. So that's our molar mass. And then oxygen, I have 1 times 16 grams per mole. Again, periodic table. And when I add them together, I'm getting 56.08 grams per mole of calcium oxide. Wow, it's amazing. Okay, so those were some of the options, right? Where you have to figure out the formula. But there are some where they give you the formula, but it's very long and very laborious. And so you just have to do a lot of multiplying. And these are what these next two examples are. So let's try the molar mass of C4H3COOH. Okay? So I come over here and I'm like, all right, I'm gonna list them all out. Okay, I have carbons, I have hydrogens, and I have oxygens. Carbons, I have 4 here, 1 here. Okay, so I got 5. Hydrogen, I have 3 here and 1 here. So 4. And oxygen, I have 2 sitting in the middle over here of this little acetate, right? So 2 oxygen. Awesome. Go to your periodic table and get your molar masses of each of these. For carbon, it's 12.01. If I multiply it out, I come up with 60.05 grams per mole. For hydrogen, it's literally just 1. 1.01 is what I'll use. Multiply it by 4 and you get 4.04 grams per mole. Last would be oxygen, which is 16 grams per mole. We've done this one so many times already. Multiply it by 2, 32 grams per mole. When I add these all together, I'm coming out with 96.09 grams per mole as the molar mass. Ta-da! As long as you know how many of each element are in the compound, you should be good. Let's try this bottom one here. Mass of, ooh, it's a big one. Mass of lead and water and hydroxide. Lovely. Oh, it's huge. All right, let's do it. Let's pick it out. So I'm gonna start with lead. I got 1, just 1. Cool. Lead's a big one, so we really only need 1. How about hydrogen? I know I have hydrogens and oxygens. So here I look at my H2O and I see that I have 4 of them. If I have 2 hydrogens per H2O molecule and there are 4 of them, I'm going to multiply 2 by 4 and I end up with 8 for that molecule. Okay. Go on over to your hydroxide, right, over here, and I do have a hydrogen inside. I will have to distribute my 2. Awesome, okay. So now I got 2 hydrogens coming out here, plus the 8 over there. That's giving me 10. Very large number, but it is what it is. All right, last step is oxygen. I'm going to do the same thing that I did. I'm going to distribute both of these little subscripts here to the oxygen. So I'm getting 4 from this one, and then I'll distribute my 2. And I'm getting 2 from this one. And so my total oxygen is 6. Nice. Heading over to your periodic table now, and you're going to multiply each of these numbers by the molar mass of the element. 207.2 for lead. Awesome. Nice, nice, nice. Hydrogen, 1.01 grams per mole. Gives us 10.1. And then oxygen, 16 grams per mole. Multiply, you get 96. When I add them all together, I'm getting 313.3 grams per mole. Beautiful. Lovely. Really got to work on my British accent, bro. All right, that is molar mass. And now we move on. So this is going to be the end of, I'm going to say end of online exam. Cool. So you've done that. Now you're going to transition over to the written portion. This is where a lot of what we've been working on the last 2 weeks is going to come in handy, okay? Especially when it comes to writing out the nomenclature, all right? And all the math. We're doing the math. This is a larger portion of the exam. Let me check to make sure this recording is still going. It's making me anxious. Just a minute. Okay, we're good. Nice. Okay. Let me take a drink. Just a minute. Lovely. All right. So, this is the start of the written portion of the exam. And it's a big old chart. A huge chart. I have made it accurate in terms of types of nomenclature and distribution of compound name versus formula. So you'll see something very, very similar to this on the exam. So we're going to go through and we're going to try to either give the formula or the compound name for each one of these. I know this video is probably already long. I don't even know how long I've been talking, but and I'm wasting more time talking. Awesome. We'll get to it. Oh, this is going to take forever to upload, but it's okay. We got this. We got this. So let's start up here, right? With the first one. Phosphorus pentachloride. I look at this and I immediately clock that I have a prefix right here, penta. That tips me off that I am probably using my binary compound CMPD naming rules, okay? That means all of these little prefixes are going to tell me how many of each element I have. So I look at phosphorus. It doesn't have a prefix. So it's just vibing. It's just P. And then I come over here and I'm like, okay, chloride. Chloride, that's chlorine. I know what that is. And then I just have to figure out what penta means. This would be a good thing to study is your prefixes. Penta means 5. So I have 5 chlorines. PCl5. Amaze. Move down to the next one. Calcium fluoride. Calcium fluoride. Well, this one's a little different. This one doesn't have any prefixes. Well, what could it be? Good question. Well, I know that both of these things have charges, and I have a metal here, and I have a non-metal here. So this is going to make an ionic compound, which means I have to know their oxidation states to balance them correctly. So looking at calcium, that's a Ca2+. I know that. It's in group 2. Fluoride is fluorine. That's all the way on the other side of the periodic table, and it has a charge of -1. So if I'm going to write my formula, I'm going to need 2 fluorines to balance out the +2 charge on calcium. So my correct formula would be CaF2. Okay, moving on. Magnesium nitrate. All right, I know what magnesium is, but nitrate, that looks a little weird. Well, if you're unsure, you can literally flip to the back page of the exam and you can find a list of the polyatomic ions. This is a polyatomic. You must know what nitrate looks like, but you know, you have a chart for it. So I go and I pull what nitrate is. Oh, look at that. Look at that. NO3-. Okay. Now I ask myself, what is the charge on magnesium? Magnesium, Mg2+, group 2, right? So I have to see how to balance these. I'm thinking I'm going to need 2 nitrates to balance out my magnesium. So when I go to write it, it's going to be Mg. I'm going to start parentheses, put nitrate inside, just NO3. You don't need the charges. You don't need the charges. You don't need them. Don't write that charge. Okay. So NO3 in parentheses, and as a subscript, I'm going to write 2. Wow. And so then this balances out. It's a neutral compound now. MgNO3, 2. All right, next one, hydrochloric acid. All right, I see acid. I immediately think, These are weird naming rules. I gotta remember them. God dang it. It's okay. We got acid. Awesome. And then I want you real quick to focus in on hydro here. Hydro means binary acid. Binary means two. Two elements only. And one of them is hydrogen. Okay? So the question is, what is the other one? I challenge you, look at the rest of the word. Hydro means it's binary. And now I gotta look at chloric. This gives you your root nonmetal. Chloric means chlorine. So my formula is just HCl, hydrochloric acid. Awesome. Now we're going on to kind of the opposite. We're moving back. Formula to compound name, okay? So I look at my formula below HCl, SiO2. And I'm like, what the heck is that? Well, look at your periodic table. Si, this is silicon. Silicon is a nonmetal. O2, well, we know O is oxygen. Oxygen, also a nonmetal. Okay? When you have two nonmetals, you are following the binary compound CMPD naming. Binary compound naming. This means that we use prefixes to tell us how many of each there are. So for silicon, there's literally only one in this compound, so you can just write silicon right here. Cool. But oxygen has two, right? So the prefix for two would be di. So I'd say di. And then I want to get my root nonmetal of my anion, oxygen. So I'm going to say dioxygen. Does that work? Dioxygen? Well, no. We must change this to dioxide. Ide is the proper ending. Oh, such an ugly E. So this would be silicon dioxide. Very nice. Move to the next one. MnO2. We've seen Mn a couple times, but just for, manganese. Manganese. Oh, I was going to say just for shits, it's manganese. But yeah, I guess I said it anyway. Whatever. Manganese! So that's the first one here. And if you didn't know, this is a transition metal. Transition metal. So it has special rules where we must have the charge in parentheses. And then we just have a regular old oxygen next to it, paired up with it, right? So I got manganese and I got oxygen. But now I have to figure out, well, if I need the charge in parentheses for manganese, I kind of got to know the charge. What is the charge? Take a look at oxygen. Oxygen is O2 minus. That looks like a plus, dang it. O2 minus. And I have two of them. So the total charge is -4 right now. If I only have one manganese, the charge must balance this -4. I'm betting it's a +4. Because that would make it neutral. So when I come over here to write the compound name, I can say, oh, it's manganese 4. That's Roman numeral for 4. And then oxide. Oxide. Don't forget to change that suffix for your anion. Manganese 4 oxide. Cool. Moving on. CCl2 4. There's a lot going on here. There's a lot. But if you see parentheses, right? You see these parentheses here? It means that you have a polyatomic in there. And a good thing about a polyatomic is it's on your table on the back of the exam. So go look at it. ClO2 is chlorite. Awesome. You got chlorite going on, okay? And then all you got to know now is, what is my cation? C is carbon. So you literally have your name written out right here. No transition metals to worry about. And you only had to identify one element. Carbon chloride. There it is. All right. Last one on this page is H2SO4. This one is on your exam. Just so you all know, it's on there. Get ready. So let's try to name it. I look at it, and I try to pick out what I know. It looks very confusing to me. Right now I can say that I've seen SO4 before, but where? Where have I possibly seen SO4? Polyatomic ion sheet. SO4 is sulfate. Wow, sulfate. So we have that. But then I look at what's attached to it, and I'm like, what the heck? Why are there hydrogens here? I don't know how to name with a hydrogen. If there is a hydrogen attached to any polyatomic, this means it's an acid. So you must remember your acid naming, okay? Acid naming, for things with polyatomics, when it's not a binary acid, would mean I'm going to look at my polyatomic, I'm going to go, okay, I got sulfate. 8 is going to become an ic ending in my acid. And I'm just going to use, then, sulfur, my core nonmetal, as the rest of the name. So I'm going to say sulfur, sulfuric acid. Sulfuric acid. It's a wonder, right? The name is simple, but I think recognizing it and naming it can be a bit difficult if we're not super familiar. So, practice that one. This one's going to be on exam. I already told you all this, but, extra reminders. Surprise, you thought we were done, but there's a whole other page to do. Yes, this is long. Take your time, seriously, because these are worth a lot of points, okay? Let me take a drink, just a minute, just a second. Amazed. All right, moving on. Second part of it. First one, lead 2 bromide. So I recognize this, and I say, oh my god, I have a transition metal, and I have a charge. Awesome. So this should be easy. This is an ionic compound. So I come down here and I say, well, lead is peanut butter. Mr. Peanut Butter. PB. And I know the charge is +2 because it's literally right here. Okay? Then I need to go to my periodic table and I got to find bromine, right? Because bromide, bromine. And I look and I see that it has a -1 charge. Wow. So to balance this, I would say, all right, I'm going to have 2 bromines up in there. When I go to write my formula, it'll be PB and then Br2. Lead 2 bromide. Amaze. Okay, next one. Ooh, this one is on your exam too. This is on the exam. Hello. Sulfurous acid. Now I will say, I'm going to scroll up, right? If you can figure out sulfuric acid, I challenge you to simply go back up, look at sulfuric acid's formula, and work your way from there. But to figure it out, I mean, let's take a try, right? It's an acid, and it does not have the prefix hydro, which to me means it's going to be a polyatomic ion plus hydrogen. Oh, I really botched that, didn't I? Plus hydrogen. Cool. So I just have to find the right polyatomic. If I break down the word, the OUS ending means that my polyatomic ends in ite. Ite, okay? So real quick, flip to that polyatomic sheet and look for something that ends in ite, whose main nonmetal is sulfur. I found sulfite, which is SO3 2-. Okay, awesome. So we have our main component. Now the trick here is I don't actually need the 2-. I will say that sulfite has a 2- charge. I'll put that over there. And I need to decide now how many hydrogens do I need to balance out a 2- charge. Each hydrogen is +1. So I'm going to need 2. So it's going to be H2 SO3. That is sulfurous acid. Okay, moving on. Gold 3 phosphate. Look at it. Beautiful. Gold. So again, this is just like lead 2 bromide. I look and I see a transition metal. Gold is AU, and I know the charge is +3. Very nice. Very demure. Then look at your second word, phosphate. Where the heck have I heard that before? Polyatomic. Flip to your polyatomic sheet, and you will find out that phosphate is PO4 3-. So this is getting real easy, isn't it? Now I have a +3 charge on my gold, -3 on my phosphate. And when I put them together, it's AuPO4. Gold 3, phosphate. All right. Ammonium chloride. Ammonium chloride. Weird. I'm not going to find ammonium on the periodic table, am I? No, I'm not. But you want to know where I will find it? Polyatomic ion sheet. NH4 plus is ammonium. Then I say, oh, chloride. That's chlorine. Chlorine has a -1 charge. So if I put them together, they already balance. So write it out. NH4 Cl. Ta-da! Ammonium chloride. All right. So moving on. We got the last 4 to go. H2CO3. What the heck? What the heck? Well, if you look up here, it's a lot like sulfurous acid, and it's also a lot like sulfuric acid. Okay, so I can kind of assume that since I see a recognizable polyatomic plus hydrogen, that this will be an acid. So to name this, I simply need to know what this polyatomic is. Oh, it's a really good thing I have a sheet of it on the back of the test. So flip to it, and you will find that CO3 is carbonate. CO3, 2-. And you obviously have like 2 hydrogens making up for that charge, right? Balancing it out. So I have carbonate. And my rule with acids is if it ends in 8, that's going to switch to an ic. And then you're just going to add the word acid. So I'm going to take my root non-metal here, which would be carbon. I'm going to say carbon, carbonic acid. See that? Carbonic acid. Wow, amazing. Okay, next one. AgCl. AgCl. Wow, what's that? Ag, I don't remember that one. That's a transition metal, and it's called silver. And I actually did find a mistake in my answer key on this one, so I'm so sorry. Although silver is a transition metal, it does have a consistent charge of +1. This is one of our static charged transition elements, all right? So because it has a static charge, you do not need to put it in parentheses. However, if you do, there is no harm against that. It's totally fine. You don't have to. I'm not going to mark you down if you do. It's fine. I don't care. My only issue would be is you adding a charge to something that doesn't need it in parentheses, right? But omitting it or not omitting it for one of these statically charged transition elements is not a big deal. Don't care. It's fine. So silver has a static charge of +1, and chlorine has a charge of -1. And so I see them together, and I'm like, okay, silver, chloride, awesome. They're balanced. And when I try to write it, I'm just going to go silver chloride, right? Because it's an ionic compound. And again, you could do the charge, you could not do the charge. Traditionally, yeah, probably wouldn't. But I keep getting conflicting answers. It's totally fine. Transition metals need charges. Okay. Second to last one, C2F8. Look at these and where they are in the periodic table, because these are 2 nonmetals. We haven't seen one of these in a while. We're going to use our binary compound, CMPD, naming rules. All right? And that means that these little subscripts here represent prefixes. So I have 2 carbons, and that would be the prefix of di. Dicarbon. And then I have 8 fluorines. The prefix for 8 is octa. Octa. And then fluorine would become fluoride. Right? Octafluoride. Dicarbon octafluoride. Nice. So the last one I see here, HF. Oh, what the heck? How am I supposed to name that? What the heck? Well, I see one hydrogen and I see one other element. That, my dear peoples, is a binary acid. Binary acid, for sure. So with binary acids, I always have the prefix first of hydro. Hydro. And then take my root nonmetal, which will be fluorine. So it'll be hydrofluorine. Oh, but wait. What goes on the end of this? It's going to be an ick. Ick ending. So I'm going to erase that fluorine and make it fluoric. Add your acid. Hydrofluoric acid. They're very small, but they are mighty to name. Okay, so that rounds out all of the rest of the nomenclature that's going to be on here, okay? The rest from here is simply math, and that is what we have left to get through. That is what we have left. So, calculations. So let me take a sip, just a minute. Okay. So, calculations. There's a bunch of stuff going on here. I am going to make a little cheat up at the top here. So I'm going to give you, well, I'm not going to give you, I'm giving you here in our practice exam, a pathway to follow. Back and forth. From grams to moles to atoms and back again. So we can start at grams. And if we want to convert to moles, we can simply multiply by 1 mole over the molar mass in grams. All right? Molar, MM equals molar mass. Very nice. And if we wanted to go further and take it from moles to, let's say, atoms or molecules, ions, particles, you know, I could go on forever. Then we can multiply again. And this time it's going to be Avogadro's number, which you will be provided on the exam, over 1 mole. I'm just going to put atoms here for the sake of it, right? Now, we can go back. We can go back the other way. If I want to go from atoms back to moles, well, I'm going to want to multiply by the opposite of that, which would be 1 mole on the top, because that's what I want, and then Avogadro's number on the bottom. Very nice. And then once I have moles, if I want to go back to grams, I would simply multiply again. This time, I would have my molar mass in grams on the top, 1 mole on the bottom to cancel, and I would get grams. So this is a method that you can follow each and every time that'll get you where you want to go. So, calculations. First one, how many atoms are there in 14.4 grams of NaCl? Big question. How many atoms? So it wants me on the far right of this pathway, and I'm starting with grams. I can follow my pathway and get through it, but I'm going to do it in steps, right? So if I have grams and I want to convert to atoms, I know eventually I'm going to run into this thing of molar mass. I need molar mass to convert. So right off the bat, I think I'm just going to go get that off the periodic table. Molar mass of NaCl. For sodium, I got 22.99 grams per mole, and chlorine, 35.45 grams per mole. If I add them together, 58.44 grams per mole NaCl. So that's the molar mass I'll be using for this first conversion here. I'm going to start with what they give me, which is 14.4 grams NaCl. I'm going to convert to moles first. So I'm going to put 1 mole on the top and the molar mass of NaCl on the bottom. When I divide these out, I'm getting 0.246 moles of NaCl. Awesome. Cool. I'm going to bring this down here, and that's going to start my step 2. So I'm going to convert from 0.246 moles NaCl, and I'm going to send it to atoms. Atoms. Wow. So I'm going to have moles cancel, so that's going to be on the bottom. And I'm going to multiply by Avogadro's number. Nice. And when I put this in my calculator, it pops out with this big number. 1.48 times 10 to the 23rd atoms of sodium chloride. And this is my answer. Wow. Nice, right? All right, let's try the next one. This one is asking the opposite question of the first one. How many grams of pure gold does 5.8 times 10 to the 24th atoms weigh? So I'm starting with atoms and I'm ending in grams. I'm going the opposite direction. So again, I will need my molar mass. I'm going to pull that out right now because it's just easier for me. And it's lovely because it's only one element. So go to your periodic table, pull that molar mass. For this one, I got 196.97. And you'll use that in the second part of our calculation. Part 1, however, I'm just going to start with what I was given. 5.80 times 10 to the 24th atoms of gold. To take this back to moles, I'm going to put 1 mole on the top. And I'm going to divide this by Avogadro's number. Yeah, I'm going to get rid of that. And so when I divide it out, I get 9.63 moles of gold. Now this is a ton of moles. I know y'all don't know chemistry yet like that. But like, this is a lot of moles. Heh. It's my calculation. It's fine. It's fine. All right, and now I'm going to take this number of moles, and that's going to be beginning of step number 2, which would be, I got 9.63 moles, and I have to take it back to grams. So I'm going to multiply this. I'm going to put 1 mole on the bottom because I want it to cancel. And then I'll use my molar mass of gold on the top. Okay? So multiplying this out, I end up with 1,896.8 grams of gold. That is quite a lot. God, I want some of that. For real. Make me a savings account. Okay. Next one. Oops. So, what is the percent composition of calcium in CaCl2? Great question. So we're going to start. Percent composition equals mass of the element I want to find out, right? In this case, it's calcium, over mass of my compound, CMPD. All right? Divide those and then multiply by 100. So, I can, first, I need to find the molar mass of CaCl2. Molar mass of CaCl2. I look and I go, all right, calcium. What is that? I got 1 calcium in here, and it is 40.08 grams per mole. Awesome. For chlorine, I have 2, and they're each 35.45 grams per mole. If I multiply that together, it's 70.9. Awesome. And then we can add these 2 numbers, and we can go, okay, how much is it? What's the total? I'm coming out with 110.98 grams per mole. That is what CaCl weighs. That is the mass. So I just have to plug these numbers now into my percent composition formula. Mass of my element of calcium is just going to be this number, 40.08 grams per mole, divided by this number, 110.98 grams per mole, and then divided by 100. My grams per moles will cancel, and I will end up with 36.15% calcium. Wait, I want to do a little thingy. Calcium! Wow! Oh my god, they keep getting messier as I go down. Whatever. So, that is your percent composition of calcium in calcium chloride. Not that bad, right? Not that bad. Let's see. What is our next one? So, this is our last one. This is the last question on the exam. And it's asking, what is the empirical formula of a compound that is 5.88% hydrogen, 35.29% carbon, and 79.9% bromine? So this is a multi-step problem. This is your biggest one. This is worth, what is it, 7 or 8 points, okay? But we're going to go through it step by step. We can do it. We just got to jog the memory. So my first step is I'm going to convert percent into grams. And if you remember, in class last Friday, I did tell you that all you had to do was turn those percentages into grams. That's it. Like, literally just take the percent sign away, slap a G on there for grams. So hydrogen has 5.88 grams, because we're assuming 100 grams in a sample. Carbon has 35.29 grams. And then bromine, we got 79.9 grams. Awesome. So I got all of those. My second step here is going to be converting from grams into moles. Because for empirical formula, I must know the number of moles to get the correct subscripts. So, to convert grams to moles, if we remember here, right, I'm going to multiply by 1 mole over the molar mass in grams. So I need to go to the periodic table and get my molar masses. Starting with hydrogen, I'm going to set this up. And I'm going to say, well, I got 5.88 grams of hydrogen. To get to moles, we got 1 mole on the top here. And I'm dividing by the molar mass of hydrogen, which is 1.01 grams. Very cool. When I divide these out, I get 5.8 because it's literally just dividing by 1. So there we go. And this is going to be moles, hydrogen. Let's do the same thing for carbon. I got 35.29 grams of carbon. I'm going to multiply by 1 mole over carbon's molar mass, which is 12.01. And when I divide, I'm getting 2.9 moles carbon. Do the same thing with bromine. 79.9 grams bromine times 1 mole over 79.9 grams of bromine. That's so funny. Same exact thing. And so you see, I'm just getting 1 mole of bromine. Cool. All right. So my step after this is I'm going to look at all of these numbers, and I'm going to say whichever one is the smallest, I'm going to divide it into everything else. I see that 1 mole bromine is smallest, so I'm going to say, all right, divide this by 1 mole, divide this by 1 mole, okay, cool. Divide this by 1 mole, okay, awesome. So my numbers pop out. I divide everything by 1. My numbers pop out. I'm getting 1 here. I'm getting a 2.9 here. And a 5.8 here. Now, rules of empirical formula naming is I need whole numbers. All of these numbers are close enough to round to a whole number. So the 1 can stay as it is. 2.9 I'm going to round to 3. 5.8 I'm going to round to 6. So all of these numbers are now going to go in my empirical formula. So hydrogen, I have 6. Carbon, I have 3. And bromine, I just have 1. You don't even have to put anything here. You can put a 1 here if you want. You do not need to. So the final formula is H6C3Br. And that is the practice test. That's it. There it is. We have gone through literal examples of everything that you're going to need to know. Please reach out to me if there are any questions. I hope this video was all right. I hope it is a good opportunity to study. And yeah, just let me know if you need anything. I'm here. Otherwise, everyone have a very good night, and I will see you soon.